ultrasound for physics. People are going to be like, this is the crispiest. Because some of those, the video that was linked to last week, or this last week's lab, yeah, that was like, I can count the pixels.
Yeah, supposedly you can record off that thing, but I've been told that it's not a particularly clear picture.
Yeah. And who knows where it gets sent.
Thank you. All right, let's hit the last topic from chapter 19. Or should I say the last topic from test 1A, or yeah, 1A. Let's go back to our parallel plate capacitor. And I connected it to a battery. That's my positive side, my negative side. And so right now the plate's going to fill up with charge. I get electrons showing up on the right-hand side, which are going to chase electrons off the left-hand side. And light doesn't blow up yet. Now, instead of doing it that way, what I'm going to do is I'm going to take this piece of wire here and I'm going to connect it there and there. What does that change?
The amount of charge distributed over the plate.
Why would it change that?
Because I guess you would be getting half at each point, and then they're gonna fill up the plate differently.
If I got half at each point, wouldn't that make a hole?
Well, yeah, but I don't know if they're like in the middle.
Well, ultimately, the plate's going to fill up until the electrons say, no, the club, we are taking no more new membership here. And so the plate's going to fill up. It's not the same as before. This actually does not change anything. Spoiler. So it gets a certain number of electrons, and we assume that the electrons on the right-hand plate are evenly distributed. So what I'm going to do now is I'm going to take these two plates and I'm just going to put a little break right there in between them. I'll make it a little bit more visible, at least if you're standing this close. So all I've done is I've broken the plates in half. Same voltage. All I've done is it now looks like 4 plates instead of just 2. Has the capacity of electrons changed?
No.
All right. So what we have here is I have 2 capacitors that are in parallel, and they equal the same capacitor I had before. Let me write that slightly differently. For capacitors, and let me see if I can actually write it in legible script. Probably no. Capacitors in parallel for capacities in parallel, the equivalent capacitance is equal to C1 plus C2 plus however many capacitors I have. What I'm saying here is that if I have a capacitor of a 3 farad capacitor here, and I have a 4 farad capacitor there, I could replace those two, that whole structure right there, with a single capacitor.
Oh, 7 farads. Or farads, as I like to call them.
Of 7 farads. It's as simple as that. We can make it more formal. I mean, this is sort of the conceptual approach to it. But I know that the capacitance is equal to Q over delta V. If I have two plates that are in parallel right there, well, I have the same voltage drop across both. Because it doesn't matter to the path that if I go this route or I go this route, if I'm going from this point to this point, the change in potential has to be the same. Or Kirchhoff's big fat liar. Or given the time, skinny, emaciated liar about to die from tuberculosis. Sorry, of the time consumption. So delta V is the same for both. So if I have two capacitors that are in parallel, and I want to add them together, I got Q over delta, let's say Q1 over delta V plus Q2 over delta V is equal to Q1 plus Q2 over delta V, which is just the total capacitance. It's the total charge that's being stored divided by whatever voltage it is across there. Earth shattering, I know.
All right.
Let's up the game.
That's for sure going to be on the test.
Oh, adding capacitors in parallel? Oh yeah.
Let's have like half the test do that. Just the same problem, like over. Don't even change the numbers, just change the question numbers. 1, 2, 3.
That's basically an all or nothing.
Do it again. Then it's going to build upside down.
I was just thinking, I've had some classes where I'd be willing to bet somebody would come up with a different answer at some point. Like a water torture?
Yes.
Any questions before I erase?
Keep it in our minds. That's it. All right. Well, let's do the test now. We have the time. I ain't going nowhere.
There's a certain temptation just to get it over with. All right. Let's talk about series. Let's hook it up to a battery. All right, so if I have a capacitor like this, I have a certain amount of charge that shows up over here, so I have some negative charge. So I get an electron on the rightmost plate, it chases an electron off of the next plate. That electron goes over to here, negative Q to Q. So I would expect the charge on all the plates to be the same, plus or minus. I know that my total voltage is got to be equal to the voltage of this, of whatever my battery is here. So if this is delta V, call this, I have a change in potential of delta V1 and delta V2. If I go around my circuit here, I'm going to gain potential of delta V. I'm going to lose a certain amount, I'm going to lose more, and I should be back to zero. Kirchhoff's loop rule or voltage rule, if I end up at the same point, the total potential difference should be zero. So I have delta V minus delta V1 minus delta V2 is equal to 0. The concept here is going to be a major one for the second test. I know that my capacitance is equal to Q over delta V. So this would be, so therefore delta V is Q over C. So over here I would have, since this would be the total voltage, this is Q divided by my equivalent capacitance. In other words, if I just had one capacitor there, that's going to be equal to Q over capacitor 1 plus Q over capacitor 2. And again, Q is the same for all of them. And so what we end up with if we divide by Q is 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus however many capacitors we have in series.
What is that subscript for the C? Not
Here?
the 1 or 2. Yeah.
EQ for equivalent.
Is that the same one as Yeah.
Yep. That should be anytime I've done EQ on this topic. The biggest mistake students make here is getting the series in parallel backwards. Let's take a look at this from a slightly different point of view. And then we'll get into the fun examples. Oh wait, cancel. All right, I have a capacitor here, hooked up to my battery. And I am, so it's got some distance in between them.
When we say capacitor, is that like just like the two plates?
Yeah, you can treat it just like two plates. And what I'm going to do is I'm going to stick another plate in the middle. It has some thickness. I'm going to just pretend it's thin for right now, but it's some thickness. So I'm going to have negative Q here. This plate will polarize, so that's Q and negative Q. Oh, try that one again. No, that's right. Q on the right, negative Q on the left, and then Q over on the left there. And this distance here, call it D1. That distance there, call it D2. So I know my total capacitance is kappa epsilon naught A over D. And all I've done is stick a metal plate in between them. And now I have two capacitors, so that's kappa epsilon naught A over D1 plus kappa epsilon naught A over D2. Yeah, I was going somewhere with this, but
Would it not just be?
oh, God. Sorry. That doesn't work on this board.
Well, that's
Which is kappa. Apparently it doesn't look to right. Kappa epsilon naught A D1 plus D2. Well, if they're equal to each other, then D over kappa epsilon naught A is equal to D1 plus D2 over kappa epsilon naught A. Just reciprocal on both sides. And this one, well, I can break that out into D1 over kappa epsilon naught A plus D2 over kappa epsilon naught A. Well, this is just 1 over the equivalent capacitance. And this is 1 over capacitor 1 plus 1 over capacitor 2. Another variation of, the derivation over there is more official. This is specifically for the parallel plate capacitor, but you get to the same result. So having a capacitor like this is the equivalent of just that.
Even though there's stuff in between, if you can add stuff in between.
As in this part right here?
Yeah.
Yeah, it's as if you're basically, those are your distances right there. Yeah, this is a nice ideal wire. There's no resistance, so charge flows. There's no change in potential across this wire. Because we can do that on a board. All right, I cut you off earlier, Jack. You about to point out a mistake over here, or speculate, or is it?
No, I was just gonna say it was like D1 plus D2 I was just thinking you could do it in one, which we did.
Okay. All right, so let's go a little plug and chug here. I have a battery. I did capacitors to make this 3 farads and this 4 farads. And I'm going to replace it with a single capacitor. What is the total capacitance?
7.
Yep. It is not 7 farads. Now it's possible when he said 7, he was coming up with some other type of unit, which is why units are important. Sorry?
What's the distance?
Doesn't matter. The equivalent, 1 over the equivalent capacitance is 1 over 3 plus 1 over 4, which is 7/12. What's the
That's what I
equivalent?
was trying to say, but I didn't know the words.
Oh, okay. Sorry, I didn't mean to lay some sarcasm down on you. So what's the equivalent capacitance?
7/12 farads.
No.
Oh,
Which is the second most common mistake.
12 sevenths?
12/7
oh, okay.
farads. It's 1 over the equivalent. And this opens up a whole new wide variety of fun little problems. See if you can contain the joy.
What in
So, in theory, you just add them all together?
Yeah, you just have to do it in the right order, in the right way. We'll make this 1 farad, 2 farad, 3 farad, 4 farad, and 5 farad.
Now, you did just draw the line to nowhere, though. So, does that matter?
When you're doing equivalent capacitance, it does matter where the leads are. This would indicate if I took, without those 2 bits right there,
Yes.
if I took my capacitance meter, and that's where I put the probes to find the equivalent capacitance, because I will get a different result here than if I did it here.
Right.
So where you place, where the leads are matters. And there's a lab that I don't know if we'll do or not, in which you're supposed to draw out a diagram, and too many times people leave something like that off because where that's placed has a huge difference on what the final result's going to be. All right. Now, one of the issues that mess people up with series versus parallel is trying to figure out what is series and what is parallel. In series, think about it just a current flowing. If I had a current flowing down here and out there, think of these as waterways. Anywhere where the water has to cross, well, the same water would cross over 2 of these, that's series. Anywhere where they have the same beginning and ending, that's parallel. What I mean by saying ending and beginning is right here. Sure. These 2 both have the same beginning and end.
So, but there, they don't.
They don't, because if the battery disappeared, this one begins and ends here or anywhere along that line. This one has those spots. But if I had water flowing here, any water that flew across that would have to also go across that. So series.
Question about the one over here. That
one on the one, yeah, that one. It's outside, so if we, I'm just thinking of water. If you go down from the top and then just go down to the right.
It would split.
Okay.
All right, so these two are in parallel. This is not in series with another capacitor, it's in series with that structure there. So you do what you can first. So I got a parallel there, let's do parallel. So what is the equivalent capacitance here?
5 farads.
All right, so I've got my waterway coming here, I got my 1 farad there, I've got 5 there, I got 4 there, and I got 5 there. All right. Now, do I have any parallel or series?
Parallel with the other 5.
The other 5?
Yeah.
All right, let's see if we can change colors here for that stunning visual effect. Okay, green, yellow, whatever. 5 has these as the leads. What else has that? Or are you talking about that 5?
That 5.
That 5. All right, so this has these points right here. What else has those?
Never mind.
So as water flows down here and splits, it's going to, some of the water is going to cross 5s, and then whatever goes across 5 has to go across 4.
So that's a series.
Series. So what's the equivalent capacitance there?
Right. Oh, 12 sevenths farads.
Is it 9?
Oh, that's a 5, not a farad.
It's not 9 or 12 sevenths or 7 twelfths.
1/5 plus 1.
Is it 20 over 9?
So yeah, ultimately that'd be 20 over 9. All right, so now we've been reduced down to, I got the 1 here, got the water flowing, cruise it along around that path, this path. And that's 20/9.
Now, because the water's flowing